Hello and welcome back to compiler programming. Let's continue where we left off yesterday, which was we have this image file header, but we now need to add image file machine MD64 or like image optional header 64. So we need to add this data structure to our code. Let's copy that out and prepare for this. So we want to allocate this stuff. This is the type. This is not gonna be the thing. Okay. Now, the funny part about all of this is even though this is called an optional header, this header is optional in the sense of like the parent file format of the executable. So every executable is a COF file, common object file format or something like this. And there it is technically an optional header, but it is not actually optional for an executable. So even though name says so, it is not really true for us. So we do need to implement it. Let's open up Pepper as well, and in particular our minimal executable, and start looking at this stuff. Now, I actually want to see the bytes, I guess. So this is the header that we implemented, and now this is the optional header. Now, there is a lot of stuff here, so let's start looking at it. Zoom a few things so we can easier see what we are doing. Okay, let's start. First, we want magic. Okay, what is the magic stuff? Magic stuff is 020b, and it is image and T optional HDR64 magic. Great. So we don't need to hard code this, and this exists in the executable. I don't think that major link conversion and minor link conversion actually matter, at least I hope not, but we will make them what they are in our file just so that it is easier to do binary diffs and seeing if anything is actually different. So major link conversion is going to be 0xe, and I'm going to say fix me remove or replace once initial implementation is done. Okay, we have the same comment for the minor link conversion. Minor link conversion, this is 1a. Okay, now size of code is going to be tricky. So size of code is where we will need to actually do assembly of our program and measure how much code we have, so how much machine code we generated in bytes, and align it to a particular alignment. I believe that this 200 in hex or 512 is the minimal alignment that 64-bit executables actually support, but this is something we can look into the future. Into right now, I will just hard code this and again add a fix me calculate based on the amount of machine code. And right now I just say 200. Okay. Next, size of initialized data. This is probably can also be much smaller. In this code, we don't have anything basically except for one constant, which is a small string. So I'm not entirely sure why they want so much initialized data. Maybe just linker or compiler has it as a minimal constant, but it's quite strange. Let's just put it that way. Again, we are gonna fix this. So for now, for compatibility, we're gonna do this, and we say calculate based on the amount of global data. Good. Uninitialized data. I'm actually not entirely certain what goes into here, but let's just say for now it is 0. And fix me figure out difference between initialized and non-init or uninitialized. Initialized. Okay, good. Address of entry point. Okay. I think we can actually get more information about this image optional header 64 if we go to MSDN. So let's do that. Image optional header 64. Yep, here you are. And there is actually a bit more information. So we have this address of entry point, and we have base of code. And okay, I got you. So the difference between these two, even though they are very similar to each other, is that technically you can lay out your code any way you like within the code section, and base of code points to that code section basically. But inside of that code section, the instruction that you're going to start executing with is not necessarily at the very top, although typically in the compiler it probably will be because of the natural way how you compile your stuff, but not necessarily. So yeah, it can be anything, but right now we can just figure this out. So address of entry point, we will copy it from the executable, from this executable, and this is 1,000, and base of code is also gonna be 1,000. Okay, base of code is there. ImageBase. What is ImageBase? The preferred address of the first byte of the image when loaded in memory. Yeah, this field is actually bigger. So this thing, ImageBase, I believe it is not really necessary for us, but again, for compatibility, we will just, or for diff stuff, we'll just type in the same thing. And the reason I say it is not important is because we encode with rep relative pointers for our global variables, and all the jumps are relative anyway, so our code is location independent, I think it's called. I'm not sure about that. But basically, we didn't care at which base address we are loaded, so yeah, it doesn't really matter what we put in here. At least that's my understanding of the situation. Okay, so this probably is the right thing, yeah. Okay. To do, figure out if we should change this. I know that we can't start at 0 because it will cause problems and it's actually reserved space, but I don't think it really matters what we really put into here. And I think it's even not taken into account. Okay, so this is going to be dependent on our compilation. So resolve to the entry point in the machine code, and this is resolve to the right section containing code. And yes, this is a lot of fix me, but it also gives us a good idea of how we are gonna change this code into something more universal. We're just gonna slowly go through this list and tick them on one by one off, and by the end of it, we hopefully will have a very good implementation of executable generation. Okay, section alignment. Basically, we have sections in our executable, right? We have a section for code, we had a section for data, and these sections have to be aligned on a certain boundary. So their sizes are round to that alignment. And you can see that happening here. So we have base of code at address 1000, and section alignment is 1000. So you have base of code like at a single alignment, but there is nothing at 0. I think another section goes at that alignment, or maybe even not. I guess what happens is you have this padding here. No. Okay, so this alignment is actually when you load executable into memory, and that will be alignment in memory. But in the file, you use this file alignment. So everything is aligned on 512 bytes, and the first one goes into here, I believe. And you have this section, but then you have another one at 400, which is this. And at 400, we actually have the our code. So you might recognize this 4883. This is essentially a move instruction, and this is probably a call, and this is int3 or something. If I can disassemble in my brain, but we can look at it more precisely. Anyway, so see, it's at address 400, and at address 600 we have something else, and this is probably debug information here, and there is also the address import table that is not at the precise alignment. So basically, I think it's at 600 we start the data section, and then we put a bunch of stuff there. But we'll get to this. This is still a bit off for us. The point is we have two alignments, and they could be the same, but they don't have to be the same. And in general, they usually, in file, you have them more compact, but in memory, you have them spread out. Okay, so we have section alignment, and section alignment is 1000. And this is actually, I think, more or less going to be constant. We don't need to change that. We might need to turn it into a variable, but we might also be able to use it just as a part of this struct. So we'll see if we need to change some things around. Okay, section alignment, file alignment, and file alignment is going to be this, right? And you can see that they are the same because size of code is stretched to be at least the file alignment in size, while in reality we only have like 15 bytes or something. Okay. Major operating system version. This is something we have to think about and make it configurable eventually, but this is so long way off that I will probably not even do anything about that. There is probably a constant that we can use somewhere. Let me look at the stuff here. Major operating system version. Well, I guess not really. But it's fine. It's okay. We'll just hardcode this. So this is 6. And then we add a fix me. Figure out if can be not hard coded. Okay, then we have minor operating system version. This is 0. Major image version and minor image version are actually completely irrelevant for us. This is basically the version of the executable, and I think for executable is really unimportant, and this is why they are 0 here. But if you have a DLL, then I guess it might be important where you can have a machine readable version of saying this is the version X of my DLL, and you can have multiple versions so you can look up them. But yeah, for us it's completely irrelevant, so we can actually even skip this stuff completely because everything else will be initialized to 0, I believe, that we don't put into this field. Okay. We do have major subsystem version and minor subsystem version, which are probably the same as operating system version. Then we have the Win32 version value. We probably don't need that one either. It's 0 here anyway. Size of image. And I think this is basically the number of sections multiplied, like the sum of the section sizes aligned to the section alignment. So we have 4 sections with like this, or maybe one of them is actually bigger. Like we will see how that works out. So, but this is something that definitely needs to be implemented, and something that we will need to figure out how to calculate. So let's say 4,000 for now, and then we say fix me calculate based on the sizes of the sections. Okay, size of headers. Size of headers is, there is actually explanation here. The combined size of the following items rounded to a multiple of the value specified in the file alignment. So we take the DOS header, we take this stuff, we take the image file header, we take optional header, and all the section headers. So essentially, like once we are doing this correctly, we will need to do whatever we are doing here. Then later here we will do sections, and then we go back and patch the size here. So we would just say optional header, what is it? This field size of headers is something, and change it. In reality, I believe it's almost always gonna be this, unless we have really a lot of sections, which we want. So again, for a very long time, it will be perfectly fine if we just hardcode this. The size of headers is this. I will do add fix me calculate correctly as described in MSDN. Okay. Next thing, checksum. Nada. Okay, easier for me. Subsystem is something I mentioned earlier. You have different subsystems in Windows, and it tells the kernel how to run your code. We will use this one. So see 3 here, and it actually even shows the constant, which is very nice of this program to be able to recognize it. So we just do the same thing. And to do, this is really not a fix me because this is more or less correct, but to do allow user to specify this. Okay. size of stack reserve, size of stack commit, size of heap reserve, size of heap commit. When we load in an executable, system sets up the stack for us, I believe. And it reserves some memory and points RSP to that memory. And in Windows terms, when you do, it does basically virtual alloc call, or there is a more low level call in the kernel, but virtual alloc just delegates to that. And in virtual alloc call, you can provide this flag saying, I want to just reserve the memory for me, or I want to actually get physical pages for that memory. So something that I can write to. And this is what these fields are. You basically say that I want to reserve, I think whatever that is, of memory, but I want to only actually commit physically way less than that. We will just copy this. I don't think it makes sense to mess with this stuff before we really need to. And we can most likely survive on this for a while until we get to the situation where at the very beginning of our program, we need, for some reason, need a lot of stack space. And yeah, it's not really something that is going to be very important for a long time. Okay, size of stack reserve, size of stack commit. And commit is just this. And the same thing for heap reserve and heap commit. Okay, heap and heap. Cool. I missed DLL characteristics. That's not good. Let's bring that in. And this one is, as you can see, it's also a combination of flags. So we can look at it. Okay. I know what some of those flags mean. I don't know what all of them mean. So this apparently means, let me bring this a bit off so you can see. This means that you can access 64-bit virtual space. Well, that is very true. We are building a 64-bit executable, so we can deal with 64-bit addresses. Honestly, I have no idea what nxcompat means. I figured it out at some point and then I forgot everything. But for now, we will put it and figure out what nx is. Next one is dynamic base and terminal server aware. Well, this is pretty straightforward. So dynamic base is exactly what I was explaining when saying about ImageBase. Basically, I think it just ignores this when loading. This was more necessary for 32-bit executables that did not do this dynamic base, but since we are doing it, and then we can just put this in. And finally, we have what? We have terminal server aware. There is no comment here, but I assume that it's just for programs running in the console. So if you have subsystem CUI, then you should also have terminal server aware, I guess. Okay, this is DLL characteristics. Now they should match what we have. Loader flags, we can check what that actually means in here, but I doubt something we need to deal with. This member is obsolete. Great, easier for us. Okay, number of RVA and sizes. Number of directory entries in the remainder of optional header. Each entry describes a location and the size. Okay, this is where we get into more interesting stuff. So let me move this here. If you look at the structure here, you have these data directories, and we need to tell basically the loader to know how much ahead it can go to read this kind of stuff. Okay. So there is 4, 8. I guess there are 16 of them if I'm calculating correctly. Oh, there are 15. Maybe there are 15 of them. But it says 16 here. So 10 is 16 because it's hexadecimal. Not sure if there is a difference in one, but maybe it's also the program is not correct. Yep. The number of directory entries and the remainder of optional header. Each entry describes a location and a size. Yeah, so this is what we have. We have yeah, these things. We have a location and the size. First is export directory, then import directory. I believe all of these are always the same ones, and we basically always need to have them. In reality, we can drop these two from the list eventually, but since we need IAT directory which stands for import address table, they have to be in this order, I think, and that means that at least till here we need to write them out. So probably it is easier to just write them all out and have this standard size for this stuff. So I think that we can more or less hard code this thing, but with keeping an eye on it later. Is 0x10, and to think about shrinking this to if possible or something. Cool. So yeah, actually you even have this member of data directory, and we can fill it in. So image number of directory entries, yeah, it is actually defined. So we can even do this right now. And here we now say data directory is, and we can go. And each of these entries is one of these things. Let me find them. Okay. Yeah, so it's just virtual address and size. We can do that. Say virtual address is something and size is something. And we need 16 of those. Ting, ting, ting. Great. We can even name them. So this is export, import, resource, exception, security, relocation, debug, architecture, global pointer, TLS, load config, bound import. Not sure what bound imports are, to be honest. Import address table. Delay import and com descriptor. I'm not sure what is the last one, because it says there are 16 of them, but then it doesn't actually tell us. Okay, so apparently it is reserved, and this is not really com descriptor, this is CLR. Okay. Good, good, good. So this one is 0 and it is reserved. Good. So we could totally just say 15, but as I said, I think it's more stable if we do it this way and just always have 16 of them. Okay. Let's get back to our code and figure out what to put in here. We have, I can zero some of them out more precisely and say that to do it like this, because we don't have. So exception data, I really would like to not put it in our code because we don't need it for now, but maybe we will need to do this. So I will leave it expanded. Security, we don't have anything. Relocation, we don't have anything because we are not an object file, I believe. And then for debug, we will need to do something. Architecture, we don't need that. We don't need global pointer. We don't need TLS. And then we need load config or bound imports. So this is fine. This one we do need, and these 3 we don't need. Okay. So now we can actually fill stuff in, and import directory is 0x20f8. Okay. And the size is 0x28. Now exception is at this address and the size is 0xc. Debug is at 0x2010 and the size is 1c. It's interesting to see that import directory and debug directory are actually in the same, they kind of overlap basically. They don't both get different virtual addresses, so that's kind of interesting. Okay, and finally IT, it's also in the same boat, and the size is 16. Cool. Okay, let's see how we are in terms of actually building this. And yeah, it doesn't like that. We have, I opened the wrong minimal file. I wanted this one. Now I need to actually zoom in again and see how we are here. Okay, let's try to build again. We are building successfully. Let's try to run this. We can run, everything is green here, but we need to figure out if we wrote it out correctly. For that, let's open another pepper and open our build thing. This is the right file. Okay, now we have more stuff. So let's start. I think we didn't look at the rich header last time. It looks the same because we just copied the bytes, but it's always good to figure out. This is actually, from what I understand, a proprietary header, and we might not even need it, but for now, let's just, like, it is the same as it is in our executable, so let's just ignore this stuff. Signature is correct. It is 4 bytes, and they are the same. File header. We have everything that is the same here, so we are making good progress. And if we made a mistake, it is probably we wouldn't actually see the entries expanded because it wouldn't be able to parse them. Okay, optional header. This is the new stuff, and this is where we need to be more careful figuring this out, if this is actually correct or not. So looks to be okay to me. Let's scroll till this 6. Okay, like so. This looks fine. 4,400, 033, and okay. So this looks good to me. Let's check out data directories as well and see how we are doing here. Put them here. That's fine, that's fine, that's fine. And that is also fine. Cool. So we are making good progress. Again, there is lots of stuff to figure out, and we can also say fix me calculate this address and size, because obviously it's not fixed. Fix me remove exception information. We might need it eventually if you want to interpolate with C++ code, but also, if I'm understanding, it took Rust till now basically to make that happen, because it's not really trivial if your own language is not structured around exceptions. Anyhow, so this is like this. It's me. Will take a while to implement. So in order to do this, we'll need to generate a bunch of debug information, and I don't think it's even this isn't even what is used by the debuggers right now. They use separate PDB files, which might reference here something, but the whole debug story is going to be a topic all in itself. I'm not even sure I'm going to cover it, but we'll see how it goes. Maybe I will. Okay, and import address table is the same fix me, and here we need to calculate the address and the size of it. Okay, so section headers. This is kind of interesting. Where are the section headers? So this gives me sections themselves. It doesn't actually Notice how all of them are 200 or 512 bytes in size. But we need to do something else, some different view on this, because this is not really useful to us. We need to know at which offsets to actually write them, and this is not helpful. Okay. Let me get back to data directories and then look at what we have there. So we are in here. We finish over here, and then there is other stuff, which are, I guess, section headers. So first you have the name of the section, And then you have some of the other fields. And I guess these are the fields. Image section header. Yeah, so these are the objects that we will need to write out. Let's take a look at them. Image section header. Okay, that's not very helpful. This is much better. Okay. Let's put this over here and we will need to write them out. Okay, so we have, first is text section. So let's do that. We again need to allocate it. So we allocate this, it is now image section. This is text section header. And we now need to fill it in. Okay, so name is, I'm not even sure this is gonna work, but we'll see. So let me try to compile this right away because I think it will complain if we do this. Image section header, image section header. Yes, it should be like this. Okay, so no, it is, I guess it is fine to do it this way. Okay, well, good for me. Next, I have virtual size or physical address. This is interesting. I guess I will need to read in MSDN when I do what. That should be written out there. Image section header. Okay, and then we have null padded TTF8 string. Okay, that's fine. Okay, so you can have longer section headers. We don't care about this. MISC physical address, the file address, virtual size. The total size of the section when loaded into memory in bytes, if this value is greater than the size of raw data member, section is filled with 0. This field is valid only for executable images and should be set to 0 for object files. Okay, since we are writing executables, virtual size actually needs to be something. And in particular, virtual size is 10 for us. And this is actually should correspond to some of the other entries, but actually that's the size of the code, I believe. Yeah, text, weirdly enough, is actually the code. Okay, so virtual size is this. And we do a fix me saying that this is size of machine code in bytes. Okay, next is virtual address. This is easy. Again, this is address of the section, virtual address, and we can actually copy it from optional header base of code. Base of code. This should be fine. Next, we have size of raw data. I assume it's going to be... okay, so the size of raw data is the size in the file. And there is also size of code here, which we can use. So we can say size of raw data is optional header size of code. Okay. The next thing is pointer to raw data. This is the offset in the file where we will write this section out. This needs to be calculated based on the size of the, so we have this stuff, where was it? Size of headers. So we can do optional header size of headers. So it will be something like U32, yeah, section offset, like this. So the first section will go after the headers, and then each section basically adds its own size to this offset, and we can then use this offset here. Okay, pointer to relocations is 0, pointer to line number 0, number of relocations 0, number of line number 0. The only thing we need to fill in now is characteristics. Characteristics is what? Image SCN CNT initialized data, image SCN memread. Okay. Image SCN initialized data, right? And memread. Okay. We can do that. And memread. It's interesting that it's not marked as executable. Is this even correct? Maybe let me recheck that the program is correct. So you have 6020 and 6000. Yeah, that's Pepper is actually wrong, because it should be mem read and mem execute, and then initialize data. That would be correct. Okay, let's try to build this. Use. I can do that. Okay. Virtual size is not a member of, so it's basically MISC. Yeah. Okay. Good. Let me quickly check this out, and this will probably be it for today. So let's run the tests. We need to close this thing. That is fine. Let's open it again, open our test, and look at the data. Okay. Unfortunately, it doesn't look like it can show the section headers until we write out all of them, or until they point to the right thing. So this is something I will do off screen, because it will be just more of the same. And then the next time we'll start writing out the actual data of the section. For now, I thank you very much for watching, and hopefully see you next time.